right, let's go ahead and get started with our first presentation of the afternoon. I am thrilled to introduce the Brigham Young University team, and they don't have an easy acronym for me to say, so I have to look. Untethered and Modular Inflatable Robot for Lunar Applications. Take it away, BYU.
Good afternoon, everyone. We are engineers from Brigham Young University as part of the Compliant Mechanisms and Research Group, and we are excited to be here in front of you today. For sustained life on the moon, large and adaptable structures are needed. For example, a mount which can move a solar panel to the direction of greatest sunlight, or a lunar crane which can move material from job site to job site or on and off of a vehicle. These machines currently exist on Earth, but they are made of metal and are heavy and bulky. And for a rocket, bulk is expensive. Here's one other consideration. What happens when a situation arises in which a new type of structure is needed? What can an astronaut do then? Well, Amazon Space Prime is not currently invented, and so the astronaut would have to wait weeks, months, or maybe even years for the next reshipment. But we, BYU Engineering, have a solution. Introducing our truss-like inflatable modular robot for lunar operations. Our design features triangular faces which can be morphed in order to twist, move, rotate, and otherwise manipulate objects attached to it. And also importantly, recognize that there is no air compressor. Air is not only a very precious resource on the moon, but a constant tether to an air supply prohibits movement. As such, our robot is designed to operate independent of an air supply. Our design has gone through many iterations, and as a part of this, we have considered multiple lunar challenges as part of the lunar environment. We believe that that the ones pictured behind me are some of the most important for the lunar operations as a part of this project. And as such, we have performed tests to assess our readiness in many of our subcomponents that you will see later on. But first, a design overview.
Okay. At its most basic level, our robot consists of mechanical rollers that roll or move along an inflatable tube. Each roller is commanded independently by an external computer to move a specified distance along its tube. And as it moves, it bends the tube or compresses it, right? That creates a bending point, which we can manipulate. And the manipulation of the position of these bending points, as you can see in this figure up there, is essential for the overall versatility and adaptability of a robot's design. Now, by combining two of these movable rollers and one stationary anchor point roller, we create a single inflated robotic triangle of our robot. Motion of either roller can change the side lengths of this triangle and thus the overall shape, and combining multiple of them creates a truss-like structure that can change its shape dynamically. Shown up here are three triangles working together to raise, lower, and tilt, and even roll in some of our testing, this octahedral shape. Now, the true power in our design lies in its modularity and its reassembling. Our robot can be, through the combination of octahedra and triangles, almost any useful structure can be created. Shown up here is our solar panel mount that has been constructed with two octahedra in our lab, and a concept for a lunar crane that could raise, lift, move, rotate, and walk along the surface of the moon.
All right. So one of the major advantages of an inflatable robot is its ability to deploy from a limited stowed volume. Here we have pictures of our stowed solar array and the inflated solar array. When stowed, the robot sits at 16 inches high, and once inflated, it reaches all the way up to 8 feet high, achieving a 6.2 to 1 deployed to stowed volume ratio. Here we also have a video of that solar array inflating. We have been able to test various stowing configurations with different bolting patterns, and we will continue to do that testing and research research process until we are able to fully reduce the human intervention necessary for full self-deployments. All right, so now that we know what the robot does, how does it do it? We will be going over the multiple components of this robot, such as the hardware, like the rollers, joints, and tubes, as well as the software for simulations and mechatronics.
All right, so as mentioned before, there's lots of challenges involved in the lunar environment, so we needed a design that was totally tubular. And so with that, we have first the material consideration of the tube itself. This has to be light, it has to be strong, it has to be able to endure a lot of UV exposure, it has to be able to deal with the effects of abrasion and dust adhesion, and then lastly, it has to be easy to work with because once again, air is a precious resource. If you have to take it apart and then recompress every single time, you're wasting a lot of astronauts' time and you're wasting a lot of their air, neither of which are very good things. And so what we did is we used polyurethane tubing because, once again, of its properties, it's lightweight, it's strong, and it has really good abrasion resistance. And so we created long tubes of these, and then in order to seal them and interact with the rest of the roller module, we invented these pucks, which you have a circumferential groove that would be, you would insert the puck into the end of the tube, you would clamp that down with an airtight seal, and then you would use this front face, the slot, and you would attach that into the anchor point on the passive roller module. With that, that means that the astronaut does not have to take apart the tube or the triangle each time you want to compress or decompress. All you have to do, because of the through valve stem, is inflate it and deflate it much as you would a bike tire. And the same thing goes for repairs. If there is a leak or anything like that, you can apply a patch.
All right, everyone. It's time for some of the hot stuff. And what I mean by hot stuff is the thermal testing, the sandblasting, and the UV rays. We decided to validate our robot by going to Autoliv, a car airbag manufacturing company. They lent us 2 thermal chambers. One was set at -40 degrees Celsius, and the other was set at 60 degrees Celsius. On your left, you can see the robot operating smoothly in -40 degrees Celsius. Later, as we noticed, the tubes were pressurized at 5 psi at room temperature, and it naturally decompressed and became stiff and brittle. And because it was stiff and brittle and pinched through this triangle, the rollers could not catch on the tube, and it led to cracking on the inner tube, which led to an air leak. We hypothesized that if we start at a higher initial pressure, or the nominal pressure, which we will talk about later, we can mitigate this problem. We've also tested this in the 60 degrees Celsius thermal chamber, and it performed remarkably well with no problems. And then on your right are some UV testing and some sandblast testing. The UV, we used UVA and UVB radiation, gave the tubes a nice little tan, and we saw that there's little to no wear on the tube material. And we also sandblasted the tubing in 10-second intervals with a high velocity blaster. And while dust did get into the tubing, we found that there was also little to no wear. Later, we hypothesized. We realized that with further research and funding, we can find a more space-worthy material to fulfill these criteria.
So for our robot, we have 2 configurations for the roller subsystem. On the left, we have the active unit, which moves the tube back and forth so that the truss may change its shape according to the kinematic protocol. On the right-hand side, we have the passive unit, which serves as a connection for the 2 ends of the tube. This connection is accomplished by attaching the pucks at each end of the tube to the passive unit. This passive unit, okay. So on the left-hand side up there, we have the mechanical architecture of the active unit. So this active unit features a Delrin chassis strengthened by an aluminum spacer. To this chassis, we have attached our PCB enclosure, which contains all of our electronics, a battery tray, which contains and protects our battery. This also provides a quick connection to the PCB, and a 65 RPM motor, which actuates the 4 rollers that move the tube. This actuation is accomplished by using a gearbox, and this gearbox contains a steel pinning gear for the motor and 4 Delrin gears for each one of the rollers. The rollers, showcased on the bottom of the slide, are 10mm steel shafts with a natural gum rubber sleeve that serves to improve or increase the traction between the rollers and the tubes. We have noticed that most of the weight of our robot comes from these rollers, and so one of our main goals was to minimize or decrease the weight of these rollers. And one of the tools that we used for that was the process of topology optimization, which we have performed on all of the chassis and all of the arm parts, and this has resulted in a significant weight reduction for our subsystem and for the whole robot.
So as Mihai just explained, from start to finish, we reduced the weight by 37% for each roller through topology optimization and just by using lighter materials, which is super important for any type of space travel. And for each for each triangle, we have 3 of those rollers, so 43% of the weight was reduced for the overall triangles, which was really helpful for us as well. So you can see here on the graph, there's a direct relationship between the pressure in the tubes and the amount of current required to actually move those rollers across the tubes. So as you can imagine, as there's more pressure in the tubes, it requires a lot more torque on those rollers, which can lead to a lot of current being drawn, which we don't want to use too much of that power. So with our changes, we found that we were actually able to get up to 15 PSI gauge pressure in our tubes, and that's really good for structural purposes for our robot to hold a solar panel or any type of machinery we can put on there. But the problem with that is we wanted to optimize the right amount of pressure so that we're not drawing way too much current than we need to. So as you can see, this dotted line here is where the the maximum pressure of our old design was at. And all the way up to 10 PSI is actually what we found to be the most optimal amount of pressure to use to not take too much current. And this took about 1.3 amps of current when we were at that pressure. And each battery in the roller is about 1,300 milliamps. So overall, we have a continuous running time of about 1 hour. And since our robot's only needing to move about 10 or 20 seconds at a time to do a certain task, especially for solar paneling when you only need to shift it slightly every once in a while to face the sun, we are able to use this robot for a long period of time with this optimization.
In order for the robot to function, there needs to be a joint at each vertex. For a single octahedron, a hinge joint works, with the hinge providing 1 degree of freedom and bearings in the stem of the rods for the additional 2 rotational degrees of freedom. However, for some of our more complicated geometries like the solar array and the crane configurations of the robot, some of the joints require up to 4 independent attachments, and so a hinge joint no longer works. To solve this problem, we pioneered a novel spherical joint design that consists of a series of panels, and you'll notice that all of the edges of the panels align with a virtual center of rotation. And this is important because if a joint has multiple centers of rotation, that adds instability and unrestrained degrees of freedom to the movement of the robot.
The limitations of the original hinge joint, coupled with the difficulties of maintaining functionality in a lunar environment, shaped the criteria that we used for a preliminary literature review. We found that existing designs didn't quite meet the requirements that we had for our robot, So after several iterations, we developed the design that you guys see on the screen right there. In this particular design, the panels, the rigid panels, are created out of, they're 3D printed, and they're connected in series with a flexible capped-on tape, allowing for flexible movement between each panel. And in later iterations, we came up with this metal design, and this connects to these metal designs connect to the rollers with these clevis pins right here, which allows the astronaut, even when wearing cumbersome astronaut gloves, to reassemble or disassemble and reassemble the truss into whatever structure is needed. They connect to the arms connect to this spherical central node, and as you can see, maybe you're not able to see from that far away, but there are up to 4 mounting locations where up to 4 arms can be connected to a single central node. And the GIF on screen shows that we get excellent translational and rotational motion from this design while maintaining the virtual center, which allows for smooth and multi-directional movement.
Okay, I'm going to talk about a little bit of why we ended up choosing this kind of metal design. Because you see with the Kapton tape and the earlier ones, we went with these compliant designs. We liked the compliance because it put our hinges one piece, as seen here with the Kapton tape one. We believe if there's just one part, it mitigates the amount of the effect of the dust. There's not as many cracks in places for the dust to get into. However, as we did our tensile and other tests, force testing, we realized the polymers, the PLA, and then the polypropylene and carbon fiber ones we didn't support the weights and forces and stresses that the robot was putting on them. So because of that, we moved this metal one, as you've seen already. And it has the same exact range of motion, can accomplish all of that. It's still super robust, super awesome. We do realize there are some issues with this, including this one is still there's still the chance of dust getting into it. One of the things we're planning on working on in the future for that is maybe design some sort of fabric sleeve to go over it so the dust can't get in there. Or kind of going back to compliance, trying to figure out a way to make a compliant mechanism that's space-worthy for these joints. Another issue that's come up recently is the possibility of cold welding between the aluminum panels and the steel pins. We're still relatively new to this subject, so we're working on developing a way which could be changing materials or going back to compliance, as we've said. But overall, we believe this joint is really effective.
The robot moves based off of a kinematic simulation. The simulation represents nodes and as the rollers and edges as the tube, constrained by a constant perimeter of each triangle. The nodes are also constrained to move. The 3 base nodes are fixed, and then the triangles have a minimum edge constraint that limits so the rollers don't collide. As you see over here on the GIF, that's not working properly, so it moves really slow. But there are 9 nodes represented here for our solar panel mount, 1 for each BYU football win this season. And it's controlled by a 3-axis joystick that allows you to select a node and move it in 3D space. The kinematic simulation works really well because we're moving at slower speeds. We were curious about the dynamics of the robot, and by putting it under a step input, we found that it reacts as a second order underdamped system. This would allow us to better understand how it moves and develop a model going forward.
To help inform future controls for the robot, we created a simulation mirror of the robot that would allow us to tune parameters and identify how the robot would behave under different situations. Specifically, in modeling this robot, we chose to create each tube as a spring and damper in parallel. This allowed us to tune parameters that would get us that second order response, as you can see in the GIF on screen, and also gave us an initial understanding of how the robot might move whenever given these different inputs. Down the road, we anticipate changing this model based on the observed behavior of the robot. Essentially, the true compliance is coming actually from the interfaces between the joints and not inherently compression and extension in the tubes. However, this initial model was still extremely valuable to give us an understanding of how our simulation could mirror our final robot without having to go through extremely complicated ground contact analysis and nonlinear joint behavior.
So now that our robot has been assembled and we have kinematics and dynamics in order to control it, the final piece of our subcomponents is the mechatronic subsystem. Our mechatronic subsystem focuses on a custom PCB which integrates an Arduino, a DC motor, a 2.4 gigahertz radio module, a 3-cell LiPo battery, and a DC motor. Our nodes communicate with each other in a branching one parent, two children binary radio structure, complete with checksum airings. And that means that if a child receives erroneous data, it can know that and re-request that data from the parent as well. A future improvement that we would like to make as well is not only sending out kinematic data to the children, but having feedback also sent back from the children to our main computer so we can log and analyze its current position versus what its commanded position is as well. Lastly, because our robot focuses so much on being modular, our software focuses on object-oriented principles and harnessing the power of C++ classes in order to make sure that the same code can be applied to different roller nodes, no matter where they are in the physical structure.
An additional objective that we identified for this project was to do outreach with our local community. Specifically, we had the opportunity to go to an elementary school in our area and instruct 2 different classes of second graders about our robot. This gave them some hands-on experience with the engineering process. We also got to show them the concept of a small to large deployable state. We also got to assemble a bunch of mini octahedrons with them, and assembling 50 of these with a bunch of second graders is an experience that most of us will never forget. It also helped us to see exactly how these projects have impacts beyond just the engineering that we're doing, but also how we could give back to our community and make an impact in other ways.
And so finally, without further ado, this is just a small summary of the movement capable by our robot. We are, as you can see here, the top face can move up and squat down for a total range of motion of 4.5 feet. Not only that, but our kinematic simulation can target individual nodes and move those as well. As those nodes move and movement is focused on that, an even larger range of motion is possible. The video is sped up by 3 times, and we believe that this speed is fast enough for the loading and unloading scenarios that we have described previously. Lastly, as well, our robot is capable of twisting and turning objects that are attached to it, such as this mock solar panel mount featuring our school's logo. We are excited about the work that has been put into this project, and we are excited to see where it can go in terms of its impact on the Artemis missions and to lunar habitation as a whole. We are BYU Engineering. Thank you so much.
Thank you, BYU, for that great presentation and very inspirational ending. We appreciated that with the music as well. We're going to open the Q&A session to our judging panel. Doug, do you have a question for the team?
Yeah, nice job, everybody. I think it was a really cool demonstration and really cool technology with a lot of different applications. My first question, and I'll get to the rest of them after everybody else, but my first question is related to you showed a demonstration at the beginning of the solar panel, kind of setting up with like 2 stories sort of thing that involves some human intervention. So can you describe like why that's required at this stage and then what you have to do to make it automated in the future?
So our original testing with this self-deployment involved a mini octahedron. So we tested different ways we wanted to stow the robot to see the best way to get it to deploy by itself. So with that mini model, we were able to spin the robot to the bottom of the floor, and it worked pretty well on the mini applications. So when we wanted to apply it to our bigger solar array, we did a similar thing, and it behaved pretty similarly to the model, but obviously some tweaking and some more testing would be necessary in order to get it to the full-scale solar array model. Does that answer your question?
Have you done vacuum testing?
We talked with the physics department in our school, and they lent us a vacuum chamber with, we can also send like a volt charge through that chamber to charge the dust. So it'd be a really good simulation of the lunar environment. Fortunately, due to time restraints, we weren't able to get to that testing, but that is definitely something that we plan on tackling in future testing.
All right, thank you.
I love the outreach. It must have been fun to play with a robot with second graders. I'm going to preempt Milena and ask an environment question. The surface of the moon goes anywhere from 100 to something like 400 Kelvin. There's a huge temperature swing, and I'm assuming, you know, the stiffness of your fabrics and the pressures of the gas are all going to fluctuate dramatically. Have you thought about that? What kind of problems it's going to, you know, what kind of wrenches it's going to throw in your design and how you might mitigate them?
Yes, we have thought about that, and I think at some point we considered having attached to each triangle a little air tank that could relieve some of the pressure if the pressure gets too high, or allow some of the pressure to be released back into the tubes during the cold temperatures. So I think that is something that we have considered, yeah.
Along those lines, so at the Autoleaf facility where they had thermal testing available, we were kind of under the limitations of two things. One, their thermal chambers, and second, we had the limitations of our prototyping materials. Due to a lot of issues with the shipping and manufacturing, we weren't able to get our hands on much space grade material, and so we were checking the thermal cycling. That's what we're testing. So we went twice to Autoleaf. The first time, we brought a couple different materials to see which ones would do best in the temperature, and we would have just one chamber. We took it hot, and then we had that same chamber cycle down, and we did that 6 times to observe how the pressure changed with those cycling, and acting pretty closely to an ideal gas, the air in the environment would expand at higher temperatures, creating more pressure, and then depressurize at colder temperatures. And so something that we would love to integrate further would be working with more space-grade materials so that we can increase the cycling of our testing beyond just that 100-degree Kelvin range that we did test. But unfortunately, we have not been able to do that at this time.
With respect to the inflatable structure, going through the rollers and also the inflatable structure in the regolith and kind of micrometeorites, as far as that durability of your mechanisms when it's kind of rolling around, kind of moving around in the regolith, what's kind of the approach to mitigate that? Is it just hoping that the materials are thick enough and durable enough to kind of, I saw you did the sandblasting, but is there additional layers, additional things that you're going to look to add to make this more durable and more resistant to micrometeorites?
Earlier in our design, we decided that maybe we could do like a multi-layer tube. So there'd be like an inner tube and an outer tube. But the biggest problem with that, since it rolled along, the rollers roll along the tube, it created wrinkles on the inside. It led to too many problems. So then we had to stick to the singular fire tube for now. But we do realize that NASA has developed a recent nanocarbon fiber, like nanocarbon tube, and they can send like some AC charge through that tube to repel dust. And it's also resistant to temperature and UV radiation. And we hope that if we did have more money and more time, we'd be able to source that material for the robot to withstand lunar regolith.
Yeah, I'll ask. Along the lines of Michael, you know, you got your wide temperature swings, and you talked a little bit about maybe having a pressure regulation system, but what is the operational pressure range that you guys can typically run? I mean, is it pretty broad, or do you have to stay within a very tight tolerance?
So what we tested this material at, we had what we called a storage pressure, which is we would just like pressurize it enough so that it could hold its shape, and that's what we would store it at for extended periods of time, and that would usually be between 3 to 6 psi, and that is what we tested thermally, because we could observe those swings a lot easier than something with a lot more pressure where it wasn't as, like the changes weren't as visible. And then when we would do deployment and other like load testing, we would test at the nominal pressure mentioned at about 10 psi. And then the max we tested with was a 15 psi as mentioned, but we were doing burst testing to see just how strong the tube and puck system was. And with that, we got up to 50 psi without yielding of the tube. The pucks had started to yield at that point, which is why we implemented the dome on the puck that we passed around. So we have a decent factor of safety running at 15 psi. We haven't run it more than that, but technically burst pressure is a lot higher than that.
And like Brian said, the highest we've run an actual roller on it is 15 psi, but the tubes could go much higher. And so at that point, it seems to me be also a function of how strong our motors are as well. And so there's that other component in it, and it shouldn't be hard to increase the strength of our motors to match a higher psi and a higher strength.
Yeah, this is a very innovative idea. Great job. And I have one comment and one question. Comment is, you test the UV, radiation test at 3065 nanometer, but actually UVC is more shorter than 200 nanometer is responsible for the polymer degradation. So maybe in the future, if you want to UV radiation test, you have to use an UVC. And 3065 is more close to visible light ranging. And question is, you already mentioned interference mitigation for the compliant joints, so that's the good. But I'm wondering if we have any similar protection idea for the gear mechanism, because that gear might be jammed by the dust, lunar dust. So do you have any idea to protect?
So yeah, for the gear mechanism, we're trying to protect it using a gearbox, and ideally that gearbox would be insulated so that dust particles cannot get in there. We haven't done that with our current prototype, just because we're working here on Earth, but we have some ideas on how to protect that using like rubber gaskets and space-graded materials. Does that answer your question? Right.
So my question is mainly about the joint that you guys have, and you'd mentioned a couple applications there. The first I think that you were looking at was the solar array kind of pointing, and then you'd also talked about a lunar crane on the surface. So I guess the question is, it obviously has a lot of maneuverability and flexibility in it, and I think in your report you were talking about, that it could get some shearing in there, some axial, you get some bending in there. The difficulty is if you're trying to use that as a structural support member, you're probably going to get a lot of deflection. So I didn't know whether you guys had done, obviously you made a metal version of this as well, but I think the challenge is that you have all of these flexible lines in there that's going to add an awful lot of movement around the joint and deflection. So it's maybe more than a comment, but I don't know if you thought about different designs that may be a little more structurally stable, or what drove you in that direction?
That is a great question. We are in the process right now of merging kind of the compliant design with the aluminum design in such a way that our compliant mechanisms research group has thoroughly explored ways of integrating those. And so it would be a compliant design like that, where it's bending compliantly along the strip through the middle, and then there are hard stops. And so the panels would be metal as well, but then there are hard stops that prevent unwanted bending and torsion and motion in general. And so we're working on that right now. Yeah.
Since everybody took my environment questions. Okay, BYU. There are so many nooks and crannies in your design that it makes me very nervous about dust. So I would like to hear your comments about how really are you thinking about the dust resiliency of your design? Because as you've read, and hopefully you read, it just gets everywhere and it's very hard to remove. So please tell me, how did you think about dust and how compatible your design would be in that environment?
Specifically with the joint, something that we've been really considering, and one of the next things we're going to move on doing is creating a fabric sleeve over the joint. So imagine the idea would be that there's fabric that goes kind of from here to here, covering all the joints, that's tight from the dust to keep the dust from getting in, and that would allow this to move. There is worries about maybe being pinched, but I think that that's some way that we can kind of figure that out with the joints as well. That's just on the joint side.
Additionally, Simon was talking about making this compliant design a little bit beefier so it can handle that parasitic motion that you were talking about earlier. And the benefit of the compliant design is that it wouldn't have, it would essentially be all one part. And so you wouldn't have as many nooks and crannies. And so if we were to do, a more flight to path sort of approach to it, we would pursue a more robust compliant design to mitigate the effects of dust getting in the joints.
Let me follow up. Aside from the rollers, aside from the joints, what about the rollers getting contaminated with dust? What's your margin? How did you think about dust accumulating on your roller?
So, like I mentioned, we're planning on using a gearbox that would be insulated with proper materials like rubber gaskets and whatnot. But we've also considered putting brushes to clean the tube as it rolls through the roller. But we found out that's not a good idea because we're actually introducing more abrasion when we have those brushes. And so we've eliminated that idea, and that's why it's not in our current design. But we've also considered adding protective flexible sheath around the rollers. Does that answer your question?
Yes, thank you.
Okay, I think that means that we can open it up to the judging panel. Anybody who has another additional question? Kevin's got one.
Yeah, I'll take one real quick. Now, NASA has great interest in offloading payloads, and originally you had your crane thing, and I was curious how much you had done on loads analysis, because when you start getting axial loads on these tubes, enhances wrinkle formation, your load capability goes way down, and so obviously there'll be axial loads on any member the way your triangular thing is. And did anybody do any load analysis? I never saw anything with any loads on it, so it would be a great test bed for doing better understanding the dynamic operation of an inflatable.
Yeah, as part of the original kinematic model, we had introduced loads, and you could actually do a little bit of FEA with the robot. And I think we had some figures in there in the proposal, I believe. But there's a pretty simple way of creating more loading conditions and then testing those.
And doing loads testing with the full-scale prototype is definitely a next step for us. A few of us did spend some time with some low-density polyethylene tubes and some 3D printed parts, suspending weights from them and inflating it and tracking the variation in pressure to lift the structures. We also are relying on the fact that on the moon, things are 6 times lighter, and so that should help with the ability to lift things up and load bearing as well.
Real quick, when you start out a project, you should have some goals, performance goals. I can lift a certain amount of payload, and then that will help drive your design, how big the tubes need to be, what the pressure needs to be, and so I didn't see a lot of that, and really any based on a use case, what our performance parameters need to be before we design and test, and so that's always critical.
Okay, I was wondering about the adhesive. You talk about there's a tight seal with the puck that you showed us. What is the seal that you're using to actually make an airtight seal?
We use a 3M product called butyl tape. It's commonly used in vacuum bagging applications, especially for debulking carbon fiber layups. We found that that was soft enough that it was able to compress and allow us to get a really good airtight seal while also having enough adhesive that it prevented the puck from shearing out. The other motivation for the ring around that plug was to give the clamp something to rest on to also assist with resisting the forces that were pushing on it. We have already seen that improperly assembled plugs have the ability to slowly pull away from that tape as pressure is applied and held. And so that was an additional motivation for the mechanical aspect. And then the butyl tape, we actually don't know as much about as we would like to, because it was kind of a miracle find in one of the shops on campus. And we've been unable to locate that exact same tape commercially so far. And so we know what the shop told us about it. We know that it's worked really well. We have not been able to find like a part number or commercial product that exactly matches that tape. Does that answer your question?
Yep, thank you.
Ryan?
With the gas, you guys talk about the urethane gas barrier. Is that integrated into the fire hose, or is it a separate layer of material that you put inside? And then kind of follow on from that, as far as repairability, you guys mentioned that the puck assembly allows you to repair kind of, what's that repair process look like for this type of a structure?
No, great question. So what the tubes that we were looking at, we're at the end of the time of the final report, we are experimenting with kind of two very similar materials, which both of them have, which I believe, do we have the sample? Anyone hold it? Yeah. Okay, I'll show that to you afterwards. But basically, so one of the ones, which was the one we used in the final report because that is the one we had in time for most of our testing, is a polyurethane polyester filament wound outer surface, and then coated into that, and then complete coating. It kind of transitions from all polyester filament wound at the top to all just plain polyurethane coating like you would find on a normal fire hose. And so with that, we had like that 100% polyurethane all the way through, and then the repairability of it, we actually, once again, as mentioned, we had some crack leaks, and so we looked at the process to fix that. And it is very similar to applying a patch to a bike tire. If you have some of that material, you basically cut out the size you need, and then all you have to do is just take the puck out and then detach that from the roller module and then apply the patch. Internally, we were using, what was the exact adhesive? I can talk to you after again, but we basically use that adhesive, you apply it just like you would a bike patch, you would let that cure, and then the pressure would hold that in place because once again, like the pressure is it's trying to push out, and so it is pushing that patch up against the face of the bike tube.
And do you have to remove the bladder, or are you limited to how far you can reach into the tube to
So yeah,
that?
you can either, there's a few things. One, you can either just turn it inside out, which we did a couple times, and that is somewhat of a labor-intensive process, especially as you get to longer lengths of tubes. Another one that you could do is you could just have a couple spare tubes, which we ended up using a lot, so you have a few spare tubes, so you could just take off one triangle from the truss structure and just replace it with another truss structure until at a later date you have time to apply that patch. You don't need to do it inside as long as you have a couple spare tubes, because once again, all you have to do is just pressurize a new one, put it on, and then work with the old one when you have the time and resources to do so.
Any other questions from the judging panel? Elena?
Could you go back to your chart where you had all of the different environments you considered and how you tested? So I'd like to poke a bit on the temperature cycling. You chose -40 to +60. Was that a limitation brought on by the system you had available, or how? Okay, sounds like it was.
Yeah, so we chose that range. The -40 was the lowest that thermal chamber could go, so we couldn't go any lower. But the 60 we chose because the electronics that we were using at the time were not protected against the heat, and they would fail at 70 degrees Celsius based on the specs. So we just decided to set it at 60 for our purposes.
To follow up then on electrostatics, How exactly did you address electrostatics with your testing? I may have missed that.
We talked to the physics department, and they have an electrostatic vacuum chamber, and they can also send like electrical current through the dust that you put in the chamber, and you can rub the tube through that chamber. Due to time constraints, we were not able to get to that testing, but that is something that we plan to test in the future.
They'll let you put dust in the chamber? We should talk.
Just real quick, I didn't see much on positional awareness of the active modules in the report. I know you had some color-coded stuff, so how accurate does that positional awareness need to be as it moves along the tube, if there's slippage or anything like that that affects it?
Yeah, in our testing, we noticed that over time it can vary. There's some can't remember. Anyway, there's some drift that it has, but each motor has a positional encoder, so it knows how far it is along the tube. We haven't had implemented any backtracking or sending that information back to the controller. That would be future steps in making the model understand where the model thinks it is, and then sending back where the robot thinks it is, and trying to merge those two to make sure they're on the same page.
And part of that issue is the software of the microcontrollers as well. So our next step would be to switch the Arduinos with ESP32s, which allow them to be dual core, because currently our Arduino's computational power is spent up with an interrupt service routine that drives the motors every 10 milliseconds, while also trying to receive information at the same time from the parent node. And so if it's too busy receiving new information, then it doesn't keep track of how many ticks is happening, and then that's what causes the drift. With an ESP32, that dual core system can just completely separate those two processes onto two different units and would mitigate that drift there.
Any other questions from the judging panel? Doug.
So yeah, looking at this again and looking at your experiment, so the sandblasting, how confident are you that sandblasting is representative of what you might see with the abrasion that you get from the lunar soil?
Yeah, so it was, we would love to do more with precise velocities. The sandblaster we had available on campus was a very old model from the 70s that we couldn't quite find an exact data sheet for. We were able to find out that it was using a garnet silicate mixture of the sand. And so we were able, okay, based off this material, which the silicate is very similar to the lunar surface, garnet, we haven't found precious stones on the moon yet, but the working with the sandblaster, we're like, okay, we're able to use that in our initial testing to eliminate from about 8 different materials to see, okay, which are the 3 that did the best, and we use that as part of our process to narrow down materials. In the future, we would love to work with a more precise sandblaster where we can actually either work with this precise velocities and particulate size, so we can do more testing with micrometeoroid impact, which is a lot smaller but a lot higher velocity, or maybe larger particles. We were using it mostly for the rubbing of the dust that it would experience either during locomotion or during deployment as it rubs along the lunar surface. And so that was our biggest qualitative test, but we would love to do more research on that given a data sheet on our equipment.
Yeah, thanks.
To follow up on that, it just sounds like that is a very conservative, aggressive test if you don't plan on using this next to the actual rocket or launch vehicle. So let's say you deploy this far away, you won't have any plume velocity type impingement with dust in your structure. But how sensitive is it to just general accumulation and the mass that the dust can add to your structure? Have you thought about that?
Yes, we have thought about that. And one thing that we noted about this material, which once again we'd love to change materials either to something, and especially we'd love to integrate a carbon nanotube electromagnetic dust repulsion system. But with that, with what we have, we noticed that the dust, even though the abrasion didn't damage the material at all, it did tend to pick up dust. Because of the outer filament wound weave, it would kind of just like very fine particulates, which is what the lunar surface is mostly, would get stuck within these, within the filament just like surface and kind of stick there. And so that is something that we would look at after about 3 minutes of the sandblasting. We would have maybe, let's see, I believe we would have about a little less than a 16th because of a gram of extra weight after that 3 minutes of sandblasting. And so there was a little bit of mass accumulation, and that is something we have to work on in the future. But for the purposes of like actual operation within the lunar surface, the sandblasting works as well as we needed it to.
I think we're actually at time. Tom, you're gonna have to find them afterwards. I think they just wanted to play with sandblasters. What do y'all think? Just kidding. Thank you guys, BYU. Let's give them a round of applause.